Welcome back to C23 Classroom channel, and this is another example for turbulent boundary layer thickness that being calculated by using empirical method. So let's say we need to estimate the maximum boundary layer thickness and the drag due to friction on the side of a ship that measures 40 meters long with a submerged depth of 8 meters, assuming the side of the ship is approximated as a flat plate. The ship travels at 10 meters per second. Use the empirical method and compare with the result using the power law models. So here it doesn't say what type of fluid, but I think everybody knows that we are talking about ships, and ships move on water. So bear in mind that we need to find the properties of water like this. And to simplify our calculation, I take density of water is as 1000, so the temperature is around 5 degrees Celsius. I think in this question it doesn't matter what is the temperature of the fluid here. So I take 1000 kilogram per meter cube for the density, and I will take all these parameter in my calculation if necessary. So same with previous solution. So we need to calculate the value of tau. So this is the value of CF, local drag coefficient. So we have a CD 1 over 2 rho u square, and we substitute all the values from the question. We could get that it is around 82.80 Pascal. We could calculate the value of u tau, which is tau naught over rho. We substitute the value that we have here, and we could say that the u tau here is around 0.288 meter per second. And then from this basic equation, to find what is the delta, we substitute all the value, and then we could say that the delta here is around 0.384 meter. Same as previous tutorial. So we could calculate the total drag coefficient here by using this equation, and we get it is around 0.001904. And we could use this equation to calculate the total drag force. We substitute the value of CD from the previous calculation here, and we substitute all the parameters here by having density is 1000, A is area, mean area that touch or being weighted by the water. So it is 40 meters long and 8 meters deep. So and then the free stream velocity is 10 meters per second. So we get 30,464 Newton. So this is the calculation by using the empirical method. So in this question too, they asked to calculate, to compare between the empirical method and the power law method. So for power law method, what we need to do is we need to determine the velocity profile first. So velocity profile is u over u. We know that velocity profile for turbulent is y over delta by the power of 1 over n, and we need to determine what is the value of n, whether it is 7, 8, 9, 10, and so on. So what we need to do is we need to determine the Reynolds number first. So we have ux over nu. So nu is the kinematic viscosity. So please look back into the table. So we could calculate it is around 263 millions. And it can be simplified as 2.6 times 10 by the power of 8. So in my previous lesson, we already discussed about this, how to determine the value of n here. So we found that the value of Reynolds number is more than 1 times 10 by the power of 8. So means that this range of Reynolds number is lay in this range. So means that bigger than 10 by the power of 8 by smaller than 10 by the power of 9. So we assume that the velocity profile for that condition is y over delta by the power 1 over 9. So what we need to do is we need to do the von Karman equation calculation by using the blast's value of shear stress. So it is given. So from the textbooks, we could get that shear stress from the blast's calculation can be determined as 0.023 rho u square nu over u delta by the power 1 over 4 here. And from the shear stress from Karman equation, we could use the equation of rho u square d theta dx, and finally we calculate the value of theta for this velocity profile. We substitute in this equation, and then finally we could simplify as 9 over 110 rho u square d delta and dx. And then what we need to do is we need to equating these two value, means the value from the von Karman and the value from the Blasius calculation. And then after we equating both shear stress value, we integral both sides, and finally we could simplify as delta is equal to 0.433x over Reynolds number by the power 1 over 6. Then we substitute the value of Reynolds number and the substitute of x, so we could get that delta is equal to 0.358 meters. So the calculation for this one is already discussed clearly in my previous lesson, so please see my previous video to get to know how to solve von Karman equation. So from here we could simplify that boundary layer thickness from the empirical method is 0.384 meters, and delta boundary layer thickness from power law method is 0.358 meters. So we have a little bit different here. So if we calculate the percentage, it is around might be 6.77%. So it shows that power law method is create a little bit lower value of boundary layer thickness. For drag force, so this is the common equation for drag force, CD 1 over 2 rho AU square, and the value of CD here is actually we need to derive by ourselves from the velocity profile y per delta by the power of 1 over 9, and we could get the value of CD here, and we substitute all the value, and we could say it is around 23,511 newtons. If we compare from the empirical method and power law method, we could say that power law method gives lower value of drag force. It is around 22.82%.